Well, greetings and welcome to this little video segment in which I'm going to try to describe how to describe electric fields around point charges. Now, this isn't the very simplest situation that you could find. In fact, probably a single point charge would be the most simple, and the next most simple might be two identical point charges. And what I've got here are 2 point charges that are both positive, but they have different amounts of charge on them, one being 4 times as charged as the other one is. I've placed them both on a horizontal axis so that they're next to each other, and you'll see why later. I've put a convenient 12 meters of distance between them. So common questions that you'd be asked about this in an AP physics class or probably any first year college course is to find the strength and direction of the field at different locations around these charges, and also to find locations where the field might be zero, if there is such a location. Sometimes you'll find that there isn't. And one thing that I've added here that I grabbed off of a website is a picture of what the field lines would look like. Now, these field line drawings have come into a little bit of disfavor in some of the AP courses, but I still find them very convenient just to visualize what you know about the field. Because the idea is if you grab a little dot like this, and we would usually refer to this little green dot as a test charge. It's a way of just getting a feel for how strong and in what direction the field is at different locations. And as you move it around in the region around the charges, whatever line of arrows you might be on shows you the direction of the electric field right there. And the density of the lines as they're drawn gives you a measure of the strength. So as you can tell here, we must be closer to a big charge over here on the right because the lines are very densely drawn together. In fact, they're 4 times as dense here around this one as they would be around this one. Now, this isn't rendered perfectly, so you don't want to go counting necessarily, but you can certainly see a stronger field here on the right than on the left. And if you go up here, let's say at the perpendicular bisector, which would be a line running vertically right in the middle of these two, the perpendicular bisector, you would see that you have a field somewhat upwards, but a little bit to the left. Now you might say, wait a minute, you're not on an arrow there. Why would there be any field? Well, keep in mind that there are infinite numbers of arrow lines that you could draw here. We just draw a representative sampling of them. So when we're in between two lines like this, we just kind of ballpark it a little bit and say that the field line would be somewhere in between those two that we're adjacent to. So why would we be up and a little bit to the left? Well, let's go over here. I might move this picture around a little bit. So we're on the perpendicular bisector, and let's just think about what the individual charges would create as far as the field there. And this big positive Q charge would create an electric field that is radially away from it and quite strong. So I'll draw it something like that. Whereas this smaller charge here would create a field that is a quarter of that strength. So it would be something maybe like that. And so when we do the process known as superposition, that's just a fancy name for let's add these two vectors together, then we will get the sum of these two, which would be something up like that. I'm drawing, can you picture those two vectors head to tail, and I'm drawing the resultant there in black. We could do that at any points that we wanted to there. So that can be as simple as giving a rough measure of the direction and relative strength, or you could actually do a calculation. Now, if you're going to do the calculation, then you're going to have to employ, this is sometimes referred to as Coulomb's law, although it's not describing the force, it's describing the field associated with any one of these charges. So each of these charges, you would calculate the strength of the field by taking K times the charge, that particular charge, the source of the field, divided by the square of the distance from that charge to wherever you placed your little dot. So we would do that here for the little charge, and we get this little vector here that would have some number. And we'd have to do it again here, and we would get something 4 times as big as long as we were the same distance away. And then, as I said before, superposition says you just add those two vectors together. So that's one kind of skill, and you could turn this into something very simple or something complex. I'm going to move this stuff out of the way and look at the next question. Where would be a location on the axis here where we might have zero field? So if we look at the equation describing how strong the field is from each of these, you notice that we have stronger fields created when you're closer to a big charge. So I think maybe looking at the figure down here on the right might be convenient. If we grab the little dot, here we go. You see when we're halfway in between them, we're equidistant from each charge, but because the charge on the right is 4 times as chargy, then we're going to get 4 times the field created by that one. That would be a leftward field, then a rightward field created by this one. That's why the net field at this location, I think you can maybe see it here, would be somewhat leftward. If we get a little too close over here, then you can see we're on a field line or between some field lines that are somewhat rightward. So somewhere in between here, there's got to be a spot where the field, the leftward field created by the big charge on the right, is equal to the magnitude of the field created by the small charge here on the left. And I'd like to use proportional thinking to consider that. Now the charges are in a ratio of 4 to 1. So these Q's are going to be in that ratio 4 to 1. So we need the R squared number to be in the ratio of 1 to 4. What that means is we're going to have to be closer to the bigger charge, closer to the smaller charge in order to compensate for the bigger amount of charge on this. So proportional thinking goes somewhat like, if we have 4 times the charge, I need something bigger here in the denominator for this one, so that when I square it, it will compensate for that 4 up there. Well, proportional thinking says you're going to have to put a 2 down here in the R, so that when you square that 2, it will give you the 4 that you need to cancel out the 4 that the numerator is going to have. Another way to say this is you're going to have twice the distance from the big charge, so maybe we can call it 2x, as you're going to have from the little charge, maybe just call that x. Now it's not a 4 to 1 ratio because there's a square in the denominator. It's just a 2 to 1 ratio. So how do you take 12 meters and divide it so that the distance from one will be x and the distance from the other will be 2x? That means you have to divide it into 3 pieces. And taking 12 meters and dividing it into 3 pieces means each piece is going to be 4 meters long. So this x here would have to be 4 meters, and this x over here would be 8 meters. And in a typical proportional thinking problem, you might not even have this number 12. They might just say, in terms of x, and you'd say, well, one would have to be twice as far as the other one is. So there's an example of how to find the 0 point. Now if you say, is that the only 0 point? Well, consider that if we move the charge over here, let's say to the left of both charges, then each of these is creating a leftward field there, and there's no way for them to cancel out. And in a similar way, if I go over here to the right of both charges, then both are creating rightward fields, and there's no way for those to cancel out. Superposition says to cancel out, we're going to have one left and one right, and that only happens somewhere in between 2 identical sign charges. Now if we have a positive and a negative, then we may be able to find a spot on the sides here where they could cancel out. That's a problem left for a different day. So hopefully this is enough to give you some guidance on how to approach these kinds of problems. You can get a little more mathematical with it, certainly, but if you refer to a good textbook or even some online resources, that might help you with any more struggles that you might have. So I hope this was helpful for you, and good luck in your studies.